Good morning, everyone. This will be the quiz solutions video for quiz 3, since everybody's completed it by now. It was due this morning at 8 o'clock. So let's go through this. This is quiz 3, and it's not drawing for some reason. Why does it do that? There we go. I always forget to do that. Make it in drawing mode. Alright, this is quiz 3. And first question asks, a Bronsted-Lowry base is defined as, and this is just a a normal little definition question, right? So that's A. It's a proton acceptor, right? That's what a Bronsted-Lowry base is. Next question, which of the following reaction respectively identifies, for the following reaction, respectively identify the Bronsted-Lowry base and the conjugate acid, right? Well, remember that the Bronsted-Lowry base is the proton acceptor, right? And the conjugate acid is the thing that will accept that will be the thing that the Bronsted-Lowry base turns into. So we see here that there's a negative sign right there, right? That means that that oxygen is missing a proton. It probably wants to take one off of this aldehyde right here, right? So if you want to, you can always draw out the protons like that, so you know that they're there. And then this minus charge, these electrons come over here and take this proton. Actually, let me do that again. I overshot it a little bit. It's very important not to overshoot your arrows, right? Like that. And then the bonds, electrons go to the carbon down there, and that makes it a carb anion on the aldehyde. And so since this is the base, this is the Bronsted-Lowry base, it's pulling off the proton. It's gaining a proton, right, on that O, which means this is the corresponding conjugate acid. So the answer is B, structures 1 and 3. Next, this is pretty easy, right? What is the conjugate base of nitric acid? It's so easy that it doesn't give you much room to even draw anything. But nitric acid is HNO3, right? And it's only got one proton to give. So, so if we have water here, okay, the electrons from the water pull off the proton, right? And then the bond between the proton and the nitrate ion right there, right, go to the nitrate. So then you're left with NO3 minus and H3O plus. So the answer here would be C. Right? Okay. This one is next here, which is the most acidic proton. Now, I don't want you to spend too much time on this one here, okay? You could do any number of things to figure out this particular answer, okay? One of them is you could go through and look it up on your pKa chart. Remember, because on your quiz, you're allowed to use your textbook and your notes. So you could use the pKa chart to figure it out, right? But that might take some time, number one. Number two, you could apply the rules for stability, right? And for a base and the lone pair, the stability of the lone pair, right, of the base. You could use those rules too. But the fastest way to answer this question is to look and see where is there an extra proton that shouldn't be there, right? And that extra proton is where that plus sign is. And how do you know that that's an extra proton? Because if you just break all this off, remember a squiggly line means that there's something else on the other side that I want to draw. What you're going to get is this, right? Which is basically an ammonium ion, right? An ammonium ion. What did it begin as? It actually began as an ammonia, right? With a lone pair. And remember that ammonia is quite happy being ammonia. quite happy being ammonia, right? So when it has a lone pair and it's received a proton from somewhere, like from an acid or something like that, it easily give up that proton because ammonia is quite stable in itself. Okay, and don't get me wrong. I mean, you know, none of these are actually particularly acidic, right? That's an alkyl hydrogen, not very acidic right there, right? And then we have a hydroxyl there. That's not very, I mean, I keep on calling it hydroxyl, but it's the same thing as alcohol. Not particularly acidic at all either, right? So the one that is going to be, oh, and then we have this one here. That's a hydrogen off nitrogen too, but that nitrogen is happy the way it is. It's already neutral, right? And this is another alkyl hydrogen, so that's not very acidic either. So the only thing that has an extra proton on it that, you know, could fall off is the one with the charge on it. Okay? So the answer there is 3. Again, don't think about it too much. Just look at the structure and be like, what doesn't fit, right? Well, an uncharged structure, you know, when there's no double bonds around, that's probably pretty stable, right? And then if there's part of it is charged, then how do I get rid of that charge? And that's probably the one that's probably the most acidic. Yeah, easy peasy. So the answer there is C. Excuse me. What best identifies this structure below? Now this is kind of tricky here because we do have protons sitting all over this cyclohexane. Alright? Because these are all CH2s. Okay? These are all CH2s. But that one there that has the positive charge on it, the carbocation, right, is actually missing a proton. Okay? But the thing is, though, it's missing a proton in such a way, because it's a positive charge, where it needs to receive electrons. Okay? And when you have just a proton out there, right, that's coming from an acid, can you do a plus charge to a plus charge? Absolutely not. Absolutely not. Right? That can't happen. You can only move electrons, and electrons are negatively charged, right? And opposites attract, right? And electrons like to go to electron sinks. So really what you're going to be doing here is, just as an example, because it could be anything with an extra lone pair, and this is a hydride ion, right? This is a hydride ion. And a hydride, all a hydride is it's a hydrogen that has an extra electron on it, right? So that's called a hydride. And now these pair of electrons can go and donate themselves to the carbocation right there, right? So what did you just do here? What did this guy just do? This cyclohexane just do? It accepted electrons. Now does that fit Bronsted-Lowry? No, because Bronsted-Lowry is about protons, right? Did it fit Arrhenius? No, that's about protons and hydroxides. So it can't be any of these. Let's say Bronsted-Lowry. Okay. So it's either got to be a Lewis acid or Lewis base, and now you get back down to your vocabulary and your basic definitions. What is a Lewis acid? A Lewis acid is something that does what? Receives electrons. And then a Lewis base is something that does what? Donates electrons, right? So what is the cyclohexane doing right here? The cyclohexane is receiving electrons from the hydride. So the cyclohexane is what? It's a Lewis acid. What letter is that? B. Sorry, heart of English. Forgot my alphabet for a second. I was like, what letter is that? Okay. The next question is another basic definition question. A Lewis base is defined as what? We just said it in the previous answer, right? It is an electron pair donator. Electron pair donor. Sorry, my phone just went off. Let's see here. Okay. All right. So, next thing we have Okay, determine if this structure right here, NaNH2, which is actually a molecule known as sodium amide, okay, would it be a suitable reagent to deprotonate each of the following, each of the two compounds, either structure 1 or structure 2? Well, I'll tell you right now that sodium amide, when you separate those out, you get the sodium cation and you get the negatively charged with an extra electron amine right there, right? And if you were to look this up in your textbook, in the chart, right? And it's my chart's right here, okay? See? It's got a pKa of 38. Holy mother, that's a really strong pKa, I mean, high pKa, which means what? It's a super strong base. Pull off all kinds of stuff, right? All kinds of stuff. So it can come over, pull off this proton, do this number here, or it could come over and pull off this proton and do this number here, which means yes, it is definitely able to pull off both protons because it's a super strong base. According to your chart, the only stronger base is an alkene, right, and an alkane, right? So it's pretty strong. Pretty strong. Let's keep on trucking. All right, so rank from the most acidic to the most basic. Or sorry, rank from the least acidic to the most acidic, right? Again, this is one of those things where you can look on your chart, and what that really means though is that you need to get to the point where you memorize at least, ranges for these different, functional groups of their pKa's, and that way you can know what is acidic or not, because you're not going to be able to use the textbook on your exam. Okay, so this right here, that's a carboxylic acid, right? Carboxylic acids have a pKa around 4 to 5. Okay, we've got a alkyl proton right here. I tried to draw a thing around it, but it's too small, right? And this alkyl proton is between an amine and a ammonium, right? Yes, between that and a carboxylic acid. So it's not going to be as strong as a base or weak as an acid as some of the regular alkyl protons are, right? Like alkane proton, right? So it's got a pKa then around 19, right? Instead of like down in the 38s and the 40s and the 50s like the other guys. It's still an alkene, it's still an alkyl or alkane proton, so it's still a pretty strong base, very weak acid, but not as strong as the other ones that are more basic than it. And then we have an ammonia here. Talked about ammonia before in the previous question. Its pKa is around 9, right? So from least acidic to most acidic, it would be 2, 1, and then 3. Which one is that? 2, 1, 3. Right there, D. Cool, cool, cool. Oops, didn't mean to do that. There we go. D. All right, for the following acid-base reaction, identify the correct curved arrow mechanism. And I don't know how it looks on your actual quiz, but on mine, because it's a PDF, like I don't even see what the answer choices are. And really what you need to be able to do is answer these questions without seeing the answer choices. That way you can pick the right answer from the answer choices. If you use the answer choices as like a clue, you will get really confused. Okay? Okay, so what's the base here? The base here, the thing that's going to take out the proton, is this hydroxyl group right here, right? Or the hydroxide. Okay? So it's got 3 lone pairs. These 3 lone pairs come over, pull off that proton, and then the bond between the proton and the oxygen goes up to fill in that carbon, no, that oxygen's positive charge, right? And that's how you get this here. So your structure, or not structure, but your arrow mechanism, curved arrow mechanism, right, will have the hydroxide electrons coming over to pull off the proton, right, and then the electrons between the proton and the oxygen will go to the oxygen. Let's see which one that is. Definitely can't be that one, because you can't have two electrons going to each other, right? Can't have that one either, because they have two electrons going away from each other there. So those are both wrong. Okay. I'll skip that one. Can't be this one because you have a positively charged oxygen, right, with a single lone pair trying to form a double bond with a hydrogen. That makes no sense, right? And then the proton going over to the, yeah, that doesn't make any sense at all. Then we have, I have no idea what that is. That's totally wrong. So in this case, you probably could just go through and circle this one because it's the only one that makes sense. All the other ones don't make any sense at all. But that's the answer right there, right? The lone pair electrons go over, tick off the proton. Electrons from the proton and the oxygen bond go up to the oxygen. So that's answer 3 is C. And then last but not least, number 10. Number 10, okay? Identify the Lewis base, okay? So the Lewis base is the thing that's going to be doing what? It's the electron pair donator, right? So the easiest thing to do here is to figure out which one has the extra electron pair that it can actually do it. The only thing that has an extra electron pair, right, is that amine group right there. That's the only thing. So that means that's the only thing that could be the electron pair donor, which means that's the what? The Lewis base. That's all you have to do with that. And that's confirmed too in the structure here because the nitrogen, right, over here, what happens is that the nitrogen's electrons go and attack this boron here. Right? I think that's a boron trihydride. I don't know. I don't even know what the name of the structure is. But it attacks that, right? And now you have the nitrogen attached to the boron, right? The nitrogen has 4 bonds to it, so it's positive, which means it lost the pair of electrons. It donated it to somebody. Who did it donate it to? The boron. That's why it's got a negative charge. So that is the Lewis base. So that's answer 2. B. B is the answer there. All right. That's it for quiz 3. I'll see you again for quiz 4 tomorrow.